Review for exam 1. And we're going to use the review document. And the first question is, which of the following should have a lower boiling point? What we're interested in here is comparison of intermolecular forces. So we see that Na2S is bonded by ionics. It's going to have a very high boiling point. HF is bonded to its neighbors by hydrogen bonding. It'll have a relative high boiling point. Ammonia is a polar molecule, so it's lower than these, but still respectable. But N2 is a nonpolar molecule. It only has London dispersion forces available. And then water, which is another example of hydrogen bonding. So your lowest boiling point is going to be nitrogen. All right. When a water molecule forms a hydrogen bond, we got slight negative on this side, slight positive on this side, positive on that side. So when another water molecule approaches, it's going to orient itself so that the negative and the positive attract. So the best answer to that one is B. Hydrogen from one molecule and an oxygen from the other molecule form the bond. Now we can move on with new stuff. New old stuff. Number 4. Which of the following statements are incorrect concerning drawing 3? Incorrect. So drawing 3 right there looks like it has a covalent bond between the chlorine and the hydrogen. So I'm thinking that it's hydrogen chloride, right? And that would be a gaseous phase. It's not dissolved in water, so it's not hydrochloric acid yet. It's hydrogen chloride gas. So the interaction among those molecules, and it's designated, it's showing you that this is negative and this is positive. Okay, so which of the following statements is incorrect? A says electrostatic interactions exist between the molecules. Is that true? Yeah. You have slight negatives and slight positives, you're going to get electrostatic interactions. And then B, the molecules find the best compromise between attraction and repulsion. That's another way of saying that they're searching for the lowest energy state. And that is also true. There is some repulsion between the negatives and the on one and the negatives of the other, or positives and positives. So they orient themselves so that their negatives and positives are close, very close together, as close as possible. So B is true. C, these molecules exhibit ionic bonding. I don't think so. We don't see any complete transfer of electrons. We only see slight differences in charge. So C is false. Since E says 2 of the above are incorrect, we have to go to D and be sure that it's true. OCS exhibits this type of interaction. So the question is giving you is OCS is a molecule, and in order to determine its structure, we need the Lewis dot structure first, and then we need to determine its geometry. So carbon has 4 valence electrons, oxygen has 6, and sulfur has 6, I believe. Yes. So that's 16 electrons. So now we're going to have carbon in the middle with sulfur and oxygen. So that's 2, 4. We have 12 left over. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, all used up. So we still don't have an octet around the carbon. Right? So I think the most efficient way, and the one that would give us the lowest assortment of formal charge, remember that was one way we decided whether it was a good Lewis dot structure, the best. The formal charge would be optimized if you make a double bond there and a double bond here. So we're looking at this and that, and then the leftover lone pairs. Okay, so we have two groups around the central atom and no lone pairs. So this is a linear molecule, right? 180 degrees. So that means we've got to look at the difference in electronegativities, which means that this side is going to be electronegative toward the oxygen, and this one's going to be electronegative. It's going to be polar, polar toward the oxygen, polar toward the sulfur. But which one is more polar? Well, what are your trends? Below and to the left is a lower electronegativity. So oxygen is going to be more electronegative than sulfur, and overall, you're going to have a polar molecule that direction. So yes, OCS exhibits this type of interaction, the polar bonding. All right. How about 6? Which best explains the following trend? 6, yeah. Well, what is the trend? What we see is an increasing boiling point, right, in K, in Kelvin terms. We also see that all of those elements are noble gases. Right? So we have no molecules to deal with. It's just the gases, just the atoms, the individual atoms. So we also see that the list is from top to bottom, small to large. And you can tell that because if you look at the periodic table, they're in order. Helium, neon, argon, krypton, xenon, all the way down. So what's happening is the atoms are getting bigger. But the atom itself is neutral. Right? So we can't blame it on any addition or subtraction of electrons. So what do we have left? Right? We can't have polarity. Right? We don't have ions. We don't have polarity. The only thing left is London dispersion forces. And the London dispersion forces explain the increase in boiling point because as the atom gets bigger, you have the opportunity, the probability that electron density will be distributed unevenly around that atom. The bigger the atom, the more room those electrons have, the more likely you are to redistribute their density in such a way as you can induce those London dispersion forces. So A is the answer. London dispersion forces explain why this trend. Let's see, we get 7 and 8 at the same time. 7. Which of the following compounds has the lowest viscosity? All right, lowest viscosity. So what do we attribute viscosity to? Well, intermolecular forces. The stronger the forces between and among the different molecules in a substance, the more viscous it is because it resists flowing. So what we want is low viscosity, which means we need something that has very low intermolecular forces. Now you can look at this in 2 different ways. First of all, you can say, all right, which ones of these are polar or ionic? And throw those out. If you've got any non-polars in there, you keep those. So what we see is, not throw them out, excuse me. Yeah, that's right. The polar ones we throw out. So what do we have here? We got water, liquid water, right? That's polar, throw it out. We've got HCl gas. That's polar, but it's still a gas, right? So we'll kind of hold that in reserve. Then we look at the others. Carbon tetrachloride. It's a non-polar molecule, right? So it should have fairly low viscosity. And that other molecule, the D, is probably, it's too big for diesel oil. It's probably some kind of grease. So it's going to have reasonably high viscosity. The other way that you can look at it is even simpler. Viscosity increases from gas to liquid to solid. And solid, you can't even measure viscosity most of the time. So liquids are always going to be more viscous than gases. So we can throw out all the liquids, keep the gases. So we got nitrogen gas and HCl gas. And since hydrogen chloride is polar, it's going to be more viscous than nitrogen. And that's how I arrived at nitrogen is the lowest viscosity. It's an interesting phenomenon. If you've ever seen liquid helium, it's the coldest substance that we can obtain in bulk. Liquid helium, it's about 4 K. When you put it in a, you know what a Dewar flask is? It's kind of like a thermos bottle. And it's evacuated between the two walls, and it's silvered to keep the heat reflected away from the substance. If you pour liquid helium into that container, it'll climb the walls and out onto the floor. It's the strangest thing I've ever seen. Anyway, let's go to number 8. For the longest time, liquid helium was the only material that would make that would produce superconductivity in any material. It had to be that cold. But now we understand superconductivity better, and we've developed materials that will be superconductive in liquid nitrogen. So when you go to get an MRI at the hospital, that big magnet that they use is cooled with liquid nitrogen. And that's great for hospitals because they've already got big tanks of it out back, right? Instead of purifying the air that they send to the rooms for the patients to breathe, they just make their own. They have liquid nitrogen, liquid oxygen tanks out back, and they mix them in the right proportions and pump those through to the rooms. Or they send pure oxygen, either way, whatever is needed. When a nonpolar liquid displays a convex meniscus. So we're talking about a liquid, and then we've got a tube here. And it shows a convex meniscus like that. It's humped like this. Which of the following explains that behavior? So A says it has a low surface tension, therefore clings to the glass. That doesn't explain it for me. What I see in active here is that, let's blow it up some, like that. So if we have a convex meniscus, what you're seeing is a battle between adhesive forces and cohesive forces. The cohesive forces tend to draw things together and increase surface tension. They form more readily, they form a sphere when they drop, You make drops out of them. Strong cohesion does that. Adhesive forces are those that attract the substance to a different substance, in this case, glass. So in this case, I think the cohesive forces are winning in a battle with the adhesive forces. And B satisfies that understanding. Now, if it was the other way around, if this were water, this is probably something like mercury. But if it was water, it'd be like this. And then the adhesive forces are winning over the cohesive forces to draw it up against the glass. Another example of intermolecular forces. All right. Take a look at 9. Which substance can be described as cations bonded together by mobile electrons? Remember that discussion? What you're talking about here is, it was our discussion about how metals bond together. Remember the electron C model had the metals, the metal ions here and here and here, and then the electrons scattered throughout. Mobile electrons. So what you need here is one of those being a metal, right? Well, it's not a compound, so D and E are out. Krypton's not a metal. It's a noble gas, even if they made a liquid out of it, which they did there. S8 is an allotrope of sulfur, right? That's elemental. But it's not a metal, it's a non-metal. So silver is the only one that satisfies. It's the only metal in that bunch that fits this scenario. All right, 10. Oh, I don't even have to move. Which of the following statements about steel is false? All right. A, it contains carbon atoms in the holes of its iron crystals. Is that true? Yep. It's known as an interstitial alloy. That is, the voids that are created in that crystal lattice, the closest packing model, the voids, we cram carbons in there. And we can do it because the voids are big enough and the carbons are small enough, they'll fit. So that's true. A is true. B, the presence of carbon-iron bonds in the alloy makes steel harder and stronger than pure iron. That's also true. So B is true. How about C? Pure iron is relatively soft and ductile because it lacks directional bonding. That is also true. D, the amount of carbon directly affects the properties of steel. That's definitely true. Consider low carbon steel versus high carbon steel. And for centuries, the Japanese knew how to use that phenomenon to make their katanas. They would forge weld soft steel in the center of the sword, and it would be wrapped with high carbon steel to give it the edge. The trouble with high carbon steel is it's brittle. So if you made the whole thing out of high carbon steel, it'd be sharp until you hit it the wrong way and it'd snap. So they put that low carbon steel in the center to give it strength and flexibility, and then put the edge on the high carbon outer layer. It hasn't been until recently, let's see, all of these are true. It hasn't been until recently that we've been able to duplicate the performance of the katana with just a single metal. We've developed alloys that would have strength and sharpness. Number 11. Which of the following statements is true about p-type silicon? So what we mean by p-type silicon is we have this closest packing model of silicon is our foundation, and then we dope it. We substitute other elements for the silicon in the lattice. And silicon has 4 valence electrons, right? So they're available to do things. And anything we substitute in there that has p-type, positive. Anything we substitute in there that has fewer electrons will give it that positive bent, because with one less electron, you have an imbalance toward the protons, the positives. So what we need is something to the left of silicon that has 1 or fewer electrons. So let's see, silicon to the left of silicon is aluminum, gallium would work, indium would work, even boron would work. It has fewer electrons in it. So it is produced by doping silicon with phosphorus and arsenic. No, it's the wrong way. That gives you an N-type, an extra valence electron. Protons are the mobile charge carriers. Can't be, right? You got to keep the protons in the atom or you change the element. Right? The protons are stuck. It does not conduct electricity as well as pure silicon. No, it does. Better than pure silicon. It's still not a conductor. Right? It's still a semiconductor, but it does conduct better than pure silicon. So none of them are true. Right? They're all false statements. All right, let's see. What else do I have picked up? A solid crystal of sodium chloride is what? Well, let's see. If we've got sodium chloride, we know that it's an ionic compound, so it's going to have a high melting point. It's going to have a high boiling point. We know that. It's going to be brittle. All ionic compounds are brittle. It's going to be hard. It's going to be very hard because those cations and anions are locked in that structure. Can't move them easily. So let's see which one fits. Is it going to be hard? So that's B or D. Okay. High melting. They're both high melting. A good electrical conductor, a poor electrical conductor. Should be a poor conductor. Again, because those ions are locked in place. They can't move. You need mobile ions to be a good conductor, or mobile electrons like metals. But if you've got an ionic compound, then it's going to be an insulator as long as it's solid. You got to turn it into a liquid so those ions can move now, or dissolve it in something and free the ions up so they can move. So D is the only right one for that one. Let's see, 1516. Which of the following has the highest melting temperature? Well, let's see, do we have any ionic compounds in there? Yeah, D. The rest of them are either molecular or atomic. Well, they're all molecular, actually. C and E are molecules of the same element, and A and B are covalent compounds. So magnesium fluoride, that's an ionic compound, and it's going to have the highest melting point of all of those. That's 16. Which of these statements is false? Diamond is a covalent crystal. Is that true? What holds those carbon atoms together? Covalent bond. From one side of the crystal to the other, just a string of atoms and covalent bonds. So A is true. B, the size of the unit cell of lithium and cesium is the same. Consider this. Lithium and cesium, if they are the same unit cell, probably either body-centered cubic or face-centered cubic, one or the other. What's the difference between the two? Lithium is a small atom. Look where it is, the top of the alkali metals. Cesium's at the bottom. It's a large atom by comparison. Why? Well, because it's got more layers of electrons on the outside. So this is going to be larger. This is going to be smaller. So the unit cell is not going to be the same size. It may be the same type, but it won't be the same size. This will be the bigger one. Okay. So that's the false one, B. The size of the unit cells is the same is not true. They're different size cells. And since we did find a false one, then E can't be true and we can stop there. You could go on and look at the others, but there's no need because we just answered the question. 17. How would you expect the melting point of carbon tetrachloride to compare with sodium chloride? Carbon tetrachloride, sodium chloride, melting point. How do they compare? Well, I would say that this would be a huge melting point and this would be a small melting point. This is an ionic compound. That's a covalent compound, but it's nonpolar. So its melting point is going to be very low. But that I got a feeling that's not going to answer the question completely. The melting point of carbon tetrachloride should be lower because sodium chloride forms an extended ionic crystal lattice, whereas carbon tetrachloride is a covalently bonded small molecule. That's a good explanation right there. We could look at B. It should be similar? No. It should be higher? No. D. It should be higher? No. E. It's not possible to say anything about their melting points without more information. Okay. So that was thrown in there just as a filler. We found our answer. $18, $19, and $20, get them both on there. A normal atmospheric pressure and temperature of 0 degrees Celsius, which phase of water can exist? At 0 degrees, right, what phases can exist? Remember the phase diagram? We got, let's see, which one is it? Pressure this way, temperature this way. And go up here to the triple point, and then you go back like that, and go up like that. So here is gas, here's a liquid, and there's the solid. Okay, so at a temperature of 0 degrees, and 1 atmosphere pressure, it'd have to be here. This would have to be 1 atmosphere. So what can exist there? Well, if you're right on the line, that means solid and liquid can exist together. Right? If you're in the space, then only the one phase can exist. But anywhere along these lines, you can get both of them at the same time. So what we're looking at is at 0 degrees and 1 atmosphere pressure. That's normal atmospheric pressure, is another way of saying 1 atmosphere. You have both ice and water together. Okay. Which of the following processes must exist in equilibrium with the evaporation process when a measurement of vapor pressure is made? We have vapor pressure in this device. It's got a cork in it. And we got liquid down here. And we got the gas phase up here. So how did it get there? At equilibrium, you got evaporation. And you got what? Condensation. They're constantly, it looks like nothing's happening, right? The level of liquid drops down to a certain point and stops, as long as you've got the cork in it. And you're developing a pressure up here, a vapor pressure, right? At some point, and at some temperature, fixed temperature, the vapor pressure stabilizes at a fixed value, and the evaporation process equals the condensation. Both those rates are balanced now. So to answer this question, which of the following processes must exist in equilibrium with evaporation is condensation, E. That's a physical equilibrium. We're going to eventually talk about, let's see, we got to get kinetics first, next chapter. And right after that, we'll go into equilibrium, chemical equilibrium. And that same idea, the balance of process rates, operates for chemical as well as physical processes. So the chemical processes, you have a reaction going one way, and then you can have a reverse reaction. Those have to balance in order to be at equilibrium. That's why we do reaction rates first. We do the kinetics, then we get equilibrium. Gives you a foundation. Let's see, I've done that one. 21. Let's see, can I get them all in there? Yeah. 21. We're doing on time. Okay, we're good. You're given the following boiling point data. Which one of the liquids would you expect to have the highest vapor pressure at room temperature? So high vapor pressure is relative to and proportional to a low boiling point. Yeah, boiling point. Low boiling point. Because we're talking about the effect that we're observing here, the boiling point, we're observing intermolecular forces. Lower temperature for boiling point means weaker intermolecular forces. And the weaker the forces, the higher the vapor pressure. Okay. So what we would want is the lowest boiling point of this group, which would be diethyl ether, 34.5 degrees Celsius, would be the highest vapor pressure, D. (22) Which of the following decreases as the strength of attractive intermolecular forces increase? Wait a minute. We just covered that one in 21. As the strength of attraction increases, the vapor pressure decreases. So 21 and 22 are like flip side of the same coin. 23. In which of the following processes will energy be evolved as heat? 23. So we're talking about what? an exothermic process. Energy is evolved. Okay. So what can we have? We have let's say a solid here, liquid here, and a gas here. And you can have going that direction, that direction. Let's see, on the outside arrow, that direction, that, let's see, that direction, this direction, or this direction. Okay. So under which one of these would be exothermic? If the substance becomes more organized, it's lower energy and gives up heat. So if you go from gas to liquid, give up heat. If you go from liquid to solid, you give up heat. That's exothermic. So if we go from gas to liquid, this is exothermic. Excuse me, wrong direction. Liquid to gas. No, I was right. Gas to liquid, exothermic. More organized. Liquid to solid, exothermic. Or solid, gas to solid, exothermic. Okay. So what are these called? Gas to liquid is condensation, right? How about liquid to solid? Let's see, solid to liquid is evaporation. No, it's melting. This is melting. This is freezing. Freezing. And gas to solid is deposition. Okay, are any of those here? Sublimation is this one. Crystallization is another word for freezing. Crystallization occurs with ionic compounds. Right. So crystallization would be an exothermic process. Vaporization, here, with this one, that's endothermic. It takes heat to make it happen. Melting would be this one. It takes heat to make that happen. All right, so crystallization is the one that's exothermic out of that list. Let's see. 25. Okay. I can't get all the answers in there. Choose the correct statement about the diagram below. Okay, if you let's look at that diagram and try to make sense of it. There's pressure, there's temperature, and we've got one line going up here. Then we've got another one going up there, kind of like that. And then we got another one going here, like that. And we're told this is liquid, this is gas, and this is solid. Okay, that's good. So this is the triple point right here, right? You have all three at the same time. And we've got a line going across here at 1 atmosphere. 1 atmosphere. Okay, that's everything that's given in that chart, I believe. All right, so let's go down to our answers. The diagram is qualitatively correct for water. Is that true? No. Water would be like this. That line would be negative slope. So that's not true. The diagram shows that the melting point of the solid increases with increasing pressure. So where's the melting point? Solid to liquid. Okay. So the melting point is on this scale against that line. So it might be here at that pressure, and it might be here at the next pressure, and here at the next pressure. So the melting point is increasing as the pressure increases. Yeah, B is true. B is true. What else do we have there? The triple point is above 1 atmosphere. No, it's below 1 atmosphere. It's down here. The diagram could represent the phase diagram of CO2. Could it? At 1 atmosphere, you should be able to go from solid to gas, sublime. So that's not CO2. Okay, the only one that's right is B. Oh, got another one. Okay, let's see. We could take that out. Clean this up a little bit. Doesn't have that. But we do have, right here is about 200 K. And right about here is 300. And 100 is about right here. Okay, how about pressure? Right in here is about a half atmosphere. 1 atmosphere is right up in this neighborhood. And then 1.5 is on up here. 1.5. Okay. So below is a diagram for a compound Q. You wish to purify a Q that was collected at pressure of 1 atmosphere and temperature 100. So it was collected. Let's clean this up. Q was collected at 1 atmosphere and 100, right? It was collected right here, right? So which direction are we going to go from there so that we can purify it by sublimation? Okay, sublimation means that we've got to go from solid to gas directly. So if we stay at this pressure and we increase the temperature, we're going to go through liquid. Can't do that. Best thing to do, I think, is to decrease the pressure and then increase the temperature. Do we have any that fit that? Lower the pressure. C says lower the pressure to a half an atmosphere and then increase temperature to 200. That would do it. That would sublime the sample. So C, yeah, C is the best answer for that one. Abandon the attempt to sublime. Nah, I don't give up that easy. I'm gonna figure it out. I used to sublime water out of samples, out of frozen plant samples. We'd collect them in the field, and we couldn't carry liquid nitrogen around with us because it was too bulky. But we'd carry these little things like this, a little bigger than that. We'd have dry ice in them. So that's minus 78.5 degrees Celsius, which is pretty good. So we collect our samples in our Tyvek bags, tie them off and label them, throw them in that container, carry it around with us. And they freeze pretty quick. And then we'd take them back to the lab, and then we dump the whole bag into liquid nitrogen to be sure they were good and hard. And then we would put the bags, the individual bags, on trays and put them in a freeze dryer. So it'd have these trays, plates in there that were gently heated, and then we'd close the door, pull a vacuum, take the vacuum way down, and that way the water would sublime from solid to gas out of our samples. And then we could take our samples from there and grind them, because they'd be water free, so they'd be nice and brittle, and stick them in bottles and throw them back in the freezer till we got ready to analyze them. Keeping the The fancy name for a freeze dryer is a lyophilizer. So the hardest part was to keeping the lyophilizers running efficiently. They had a tendency to break down. I had one spring a leak in a Freon line, because the way it was manufactured, the line was too close to something else. And when you start those motors up, there's a vibration. And eventually that copper line wore a hole in it. And the company would not honor warranty. So needless to say, we never bought from that company again. So now we're moderate. Okay, those were the easy ones. Now we got some moderate difficulties. Number one. Okay, which of the following, and we're still in chapter 10. Which of the following is the correct order of boiling points for KNO3, CH214, C2H6, and neon? Boiling points for KNO3, CH3OH is methanol, C2H6 is ethane, and neon. Okay. So which one's going to be the lowest boiling point? The noble gas, neon. So we're going to put them in order, I guess, increasing boiling point, because the way the carets are in the answers. So this is the lowest boiling point. What's the highest boiling point? That ionic compound right there. Oops, other way around. Okay. So now we need, what do we do with these guys? All right. Which one of these is the lower boiling point? Well, ethane is a nonpolar molecule. Right. Each one of these is hydrogen. So you can see around each one of these central carbons is a tetrahedron. So even if it were polar bonds, which is slightly polar, they all cancel each other out. So that's a nonpolar molecule. It would be the next one. And then this one has hydrogen bonding. Right, CH3. In fact, if we write it molecularly speaking, like that. So there's your hydrogen bond. And it should be neon, ethane, methanol, and potassium nitrate. That's D. Let's see. Assume 12,500 joules of energy is added to 2 moles of water as an ice sample at exactly 0 Celsius. The molar heat of fusion is 6 kilojoules per mole. Heat of fusion is how much heat does it take to melt the solid to ice at its melting point. Right, so at 0 degrees, it would take that much energy to change a mole of water from ice to liquid. Specific heat of liquid water is 4.18, and the molar heat of vaporization is 40.6 kilojoules per mole. Okay, so I think a diagram would be useful here. Remember when I drew this one? So as the, this is added heat, that direction. And this is temperature. So as we add heat to solid ice, it's going to go up like that. And then when it gets to its melting point at 0 degrees, it's going to stop. Temperature won't rise anymore as long as you've got ice and water together. Once all the ice is melted, then the water starts heating up again until you reach the boiling point. Here. Then the water is going to boil at 100 degrees and stay there until all the water is vaporized. And once it's vaporized, the vapor starts the steam. You can heat it up some more. Okay? So where are we when we start? Water as an ice sample at 0 degrees. So we're starting right here. Okay? So all we have to do first, we're not gonna heat the water up. We're not gonna heat the ice up. The ice is already 0 degrees. We're gonna melt it. So this is where we have solid goes to liquid. And that's where we need the heat of fusion. And the heat of fusion is 6.02 kilojoules per mole. Okay. So how much heat do we have to start with? We have available 12,500 joules to begin with. So how much heat is it going to take to convert 2 moles of water, 2 moles of water, or ice, 2 moles of ice, to liquid at that temperature? Well, it's 6.02 kilojoules per mole, right? So we're going to end up with 12.04 kilojoules. That's how much heat we've used up. But we're starting out with joules, not kilojoules. So how many joules is a kilojoule? Well, 12,040 joules. So we've used up 12,040 joules. So we have left 460 joules. Okay, now we can use 460 joules to heat the liquid water. And to do that, we need the specific heat of water, 4.18 joules per gram degree C. Per gram degree C. Okay, that's why the parentheses says 36 grams is 2 moles. All right, so 2 moles works for this one, but now we need 36 grams of water times its specific heat, which is 4.18 joules per gram degree C, and then change in temperature. Right, that's the unknown. And this is the amount, let's put it on this side. The amount of heat we have available is 460 joules. Right? That's the equation. Remember thermochemistry last semester? Heat, actually it wasn't delta H. We called it Q, didn't we? Q, the heat, is equal to the specific heat of the material times the mass times the change in temperature. All right, so we've got change in temperature here to solve that one for. All right, so if we say this one divided by that one and then divided by this one, we get the change in temperature. All right. $460 divided by 36 and then divided by 4.18. So I got 3.1 degrees. So it's only going to go up 3.1 degrees after we use up that. So from 0 to 100, we've only gone 3.1 degrees. Okay. So it's still liquid. It's all liquid. And that would be C. There's only water, only liquid water in that sample. Okay. Yeah, see, that was 4. Oh, difficult. Okay. We can do that. Difficult number 1. All right. A crystal was analyzed with X-rays. I smell Bragg equation. Crystal was analyzed with X-rays, a wavelength of 2.33 angstroms. So the wavelength we're using is 2.33 angstroms. I'll tell you what an angstrom was. I haven't told you that yet. An angstrom, 1 angstrom is equal to 10 to the minus 10th meters. Okay. The angle of the first order diffraction, where n equals 1, if n equals 1, then the angle theta equals 19.2 degrees. What would be the angle of the second order? So if n equals, okay, just a bunch of boxes fell over with breakable parts inside. I'll leave that to our physics professor. What we're looking for here, if this is theta 1, then theta 2 is equal to something. We don't know what it is. That's the question. Okay, so we need the Bragg equation, and it should be in useful information. All right, there it is, Bragg. N lambda equals 2d sine theta. N lambda equals 2d sine theta. Okay, so we can do this in 2 steps, right? We know n is equal to this. We know the first order angle is 19.2. We know the wavelength is 2.33. So then we can solve for d. And once we have d in that same crystal, it's not going to change. It's going to be the same for the second one. So then we can put whatever we get here back in there, and then we can put in the same wavelength, and then we can put a 2 here and solve for theta. Okay, so that's the order of business. The other way you can do it is you can set up 2 equations and solve one for d and substitute the equivalent of d into your second equation, and then do the whole thing at once. And that's a little hard to follow sometimes. So let's do it 2 steps. So this is going to be 1 times 2.33 angstroms equals 2d sine 19.2 degrees. Okay, so we're going to solve for d. That means we've got 2.33 on this side, and we're going to divide by 2 because it's multiply on that side. And then we're going to take the sine of 19.2, and if I can find it here, and divide that into this. The sine of 19.2 is 0.3289, but I'm going to take it here and divide it into that. Let's see. Yep, they're in the right order. And that's 3.54 angstroms. So D equals 3.54 angstroms. All right, so now we can set up our new equation. N now is equal to 2. And the wavelength is the same. And then we've got 2 over here times 3.54 angstroms. And this is sine theta 2. So now we just solve for that one. So in order to do that, we get this one over here. And by the way, the 2's cancel. So we just divide 2.33 times 3.54. And that's 6582. 0.6582 equals the sine of theta. So how do we get theta out of that? We take the arc sine of this value on your calculator, sine, and then above it, the function t above sine should be a sine, arc sine, which is, it's not strictly speaking inverse, but it's kind of the reverse direction. It tells us what this one is if we take the arc sine of that one. Or you could write it like this. Theta 2 now is equal to the arc sine of 0.586066582. So that's what I'm going to do. I'm just going to punch the function arc sine key and find it's 41.2 degrees. Okay, so the second order maximum wavelength occurs at 41.2 degrees, which is B. B is the closest one. That says 41.1. Pick the best answer. Okay. Let's see. Next is number 2. And we're still in chapter 10, and I'm already into our second hour. So I better get a move on. So 2 says chromium metal crystallizes as a body-centered cubic lattice. Chromium is a body-centered cubic lattice. So there's going to be chromium in the middle. Right? Then we're going to have chromium at each corner. There we go. 1, 2, 3, 4, 5. Oops, one more at this corner. There we go. All right. The edge length. Oh, excuse me. I was looking at the wrong one. If the atomic radius of chromium is 1.25 angstroms, so the radius is 1.25 angstroms. Okay. What's the density of chromium in grams per cubic centimeter? So we're looking for density equals something in grams per cubic centimeter. So what do we need to know to do density? We need to know the mass and the volume associated with that mass. So I think the simplest way to do this is, what's the volume of that cube? And then how many atoms are assigned to that cube? Right? How many atoms in a body-centered cube? You got 1 in the middle, belongs to that cube and none other. But you've also got 8 corners. And each one of these chromiums at the corner belongs to 7 other cubes. So only 1/8 of it is here. That means you've got 1 here and you got 1 there. So you have 2 atoms. 2 atoms per cube. Okay. How about, we'll use that for the mass. How about the volume? For the volume, we need that length, the cube, the edge length. So how do we find the edge length of a body-centered cube? Well, useful information. Right, go to the back. And body-centered cube, BCC edge equals 4R divided by square root of 3. So that A equals 4 times the radius of the atom divided by the square root of 3. Okay, so we can say the radius of the atom is 1.25 angstroms. We have 4 times 1.25 angstroms divided by the square root of 3. So let's see what that is. .8868. Okay, and this is angstroms. Okay, so we have two approaches for the volume here. We can go ahead and cube this because it's an edge length. Cube that and give us cubic angstroms, or we can convert it to centimeters and then cube it. So angstroms, we know that the relationship of angstroms is 10 to the minus 2. 1 angstrom is 10 to the minus 10th meters. And then we can convert meters to centimeters, because we know that 100 centimeters in a meter. I think that's the simplest way to do it. So this would be 10 to the minus 8. It'd be 2.8868 times 10 to the minus 8 centimeters. And then the volume is equal to that cubed. So it's still in my calculator. I just need to, let's see, enter. Yep. So I got that in my calculator. Now just cube it. Let's see. And 3. There we go. 2.4056 times 10 to the minus 23 cubic centimeters. Okay, that's the volume of that cube. Now we need to say, all right, we've got 2 chromium atoms in there. What's the mass? So here we have 2 chromium atoms. And we have 6.022 times 10 to the 23rd atoms per mole. I got rid of the atoms, now we're moles. The reason I went to moles is because the only way I can get the mass is to go through molar mass of the element. So 1 mole is how many grams? It's easier for me to look it up here. Chromium, 51.99, 52.00. 52.00 grams per mole. Okay, so that will give us the mass for that volume. So we have 2 atoms divided by 6.022 times 10 to the 23rd and times 52. So I get 1.727 times 10 to the minus 22 grams. So we need grams per cubic centimeter. We just say this divided by that, because this is the mass. And I get 7.18 as density. Grams per cubic centimeter. Is that on there? Yeah, it's B. 7.18. Did you see the jump I made? Mass divided by volume. Okay. Sometimes I skip steps and it messes with my students' minds. All right, we're finally into chapter 11. My chapter 11. I think I need to get a new marker. This one's it's kind of fading out. How about a blue? Okay, this is chapter 11 easy. Easy. And number 1. Okay. In a 0.1 molar solution of sodium chloride in water, 0.1 molar sodium chloride aqueous. All right. Which one of the following will be closest to 0.1? All right, we can go through and calculate every one of these. Mole fraction, mass percent, and molality. But since this means moles per liter of solution, and molality means moles per kilogram of solvent, moles are going to be the same. The liter of solution, since this is very, very dilute, then a liter of this solution should be a kilogram or very close. So it's very close to a kilogram, and molality is going to be the closest approximation to molarity under these circumstances. I'm just trying to save time so that we don't have to do all the other calculations. Two, which of the following concentration measures will change in value as the temperature of the solution changes? All right. So what is affected by temperature? Is mass? No. It's number of moles, number of particles? No. Volume is affected by temperature. So which one of those has volume associated with it? Molarity. That's why D is the one that's affected by temperature, and why we don't use it in our experiment today. We use molality in our experiment because it's unaffected by temperature. About 3. Which of the following chemical or physical changes is an endothermic process? I thought we've been around that barn already. Endothermic. So an endothermic process goes from more ordered to more disordered, from ordered to disordered. We add energy. So the evaporation of water, yeah, you got to put energy in. That's a good answer. Combustion of gasoline, exothermic. The mixing of sulfuric acid in water, that's very exothermic. That's why we say, do as you ought to add acid to water. Because if you add a little bit of acid to water, then the heat of solution in that little bit of added acid will be spread throughout a large volume of water. It'll absorb the heat better. If you add water to acid, then the large amount of heat that's evolved from that boils the water instantly, and it splashes up in your face. Mixing of sulfuric acid, freezing of water. Freezing of water goes from liquid to solid. It's from disordered to more ordered. That evolves heat. So the only one that is endothermic is the evaporation of water. A. Four. Let's see. Which statement about hydrogen bonding is true? Okay, what do we need for a hydrogen bond? Let's approach it that way. Then we won't have to read through every one of them. Hydrogen bonding is effective as a dipole interaction, first and foremost. But it's a special type. You need an electronegative atom here bonded to hydrogen, and then it can be anything else over here. And this X can either be oxygen or nitrogen or fluorine. They are electronegative enough so that we can get a very polar bond this direction. This is going to be positive and this is going to be negative. Okay, let's see if which ones fits that. Hydrogen bonding is an intermolecular attractive force between two hydrogens. Nope. Hydrogen bonding capabilities of water molecules cause 1, 2, 3, 4 butane. That's the first compound. Butane to be more soluble in water than, no, butane's nonpolar. Methanol has hydrogen bonding, so it's the other way around. C, hydrogen bonding of solvent molecules with a solute will not affect the solubility. I beg to differ. It's very effective at solubilizing molecules if there is hydrogen bonding interaction. Hydrogen bonding interactions between molecules are stronger than the covalent bonds within the molecules. What would happen if that were true? The molecule will get ripped apart, right? If the intermolecular forces are stronger than the intramolecular forces holding the molecule together, molecule can't exist. It just gets torn apart. It's like those astronauts on, what was that movie? Mission to Mars, where they found that face on the surface of Mars. Have you ever seen that movie? Oh. So they bounced radar off of the image and it set a defense mechanism in place from the civilization that had left it there. And this big tornado came out of the top of it and whipped around and picked up the astronauts, and they went into that tornado and they went spinning around until they flew off in all parts. That's what would happen to the molecule if the intermolecular forces were stronger than the covalent bonds holding it together. Just rip it apart. So hydrogen bonding E arises from the dipole moment created by the unequal sharing of electrons within certain covalent bonds within a molecule. That's as close as you're going to get. That's non-specific. Here we've given it some specifics, but E is the best answer out of that group. How about number 5? Which of the following favors the solubility of an ionic solid in a liquid solvent? Well, let's see. We want to favor the solubility of the ionic solid in the liquid solvent. A large magnitude of the solvation energy of the ions. All right. Remember when we were talking about the 3 parts that go together to solubilize the solvent process. This is the heat of solution, total heat of solution. This one we said was separate solute molecules. This one was separate solvent molecules. In other words, make a whole. And this one was form solute solvent bonds. Okay. What they're talking about solvation energy is this, the formation of those bonds. So if that is if a large magnitude of solvation energy of the ions alone, does it favor the solubility? Well, you can't tell until you know how much energy you had to put in over here. So it's not the best answer, but it's part of an answer. A small magnitude of the lattice energy of the solute. Lattice energy of the solute is how much energy does it take to break the bonds, right? Lattice energy. So if it's small, you can get them apart real easy. A large polarity of the solvent. The large polarity of the solvent is going to make this pretty high, but it's also, when it interacts over here, it's going to make that high. So they sort of counterbalance. So all of the above contribute to the solubility of an ionic solid in the liquid solvent. Okay, that's why I think D is the best answer. All of those are effective. Okay. All right, do we have time to do this one? Maybe I'll come back to 6 if we have time, because it takes a little work to get that one done. So let's hold 6. In fact, I don't know why 6 is in the easy section, because it's not easy. We'll come back to it. Let's get 7 and the others done. Use the following diagram of gaseous solution. Gaseous solute in equilibrium with a solution to help answer the questions. So if you've got a solvent and your solute is a gas, what happens when you push the piston down? This will cause the pressure of the gas to increase and the concentration of the dissolved gas to go down. No, it's the other way around. It'll cause the concentration to go up. That's Henry's law. The higher the pressure, the higher the concentration of the solute in the solution, if it's a gas. This will cause the pressure of the gas to decrease and the concentration of the dissolved gas to go down. No, the dissolved gas goes up. So it's got to be, C is the only one that fits, isn't it? Oh, wait a minute, there's an E. Pressure. This will cause the pressure of the gas to increase and the concentration of the dissolved gas to go up. And the concentration of, yeah, it'll increase the pressure, so that causes the solution concentration to go up. Yeah. We found our answer, C. When you compress that gas, right, we know from Boyle's law, when you add pressure to a gas, it decreases the volume. Or we decrease the volume by this way, it increases the pressure. And the pressure then causes more gas to be dissolved in the liquid. So C is the answer to that one. How about 8? 8. Which of the following correctly states the relationship between temperature and the solubility of a substance in water? All right. If it's a solid, it generally increases the solubility. If it's a gas, it generally decreases the solubility in water. So which one fits that? C, the solubility of a substance in water with temperature cannot be accurately predicted. Well, yeah, that's true, because some solids are less soluble as the temperature goes up. Right? And we've not been able to develop a theoretical explanation for why that is. There have been some proposals, you know, but still it's an empirical observation. Okay, 10. This one looks bad, but it's really not. A solution contains 1 mole of liquid A and 3 moles of liquid B. So we got this solution, and it has 1 mole of A and 3 moles of B, right? Yeah. This solution has a vapor pressure of 314 torr at 25 degrees. So the total vapor pressure right here is equal to 314 torr. Okay. Still at 25 degrees, pure A has a vapor pressure of 265. So PA equals 265 torr, and pure B is 355 torr. Okay. Which of the following is true? Well, what's the contribution of A to the total? It's 1/4, right? Because we've got 4 moles total. 1/4 of them are A. So 1/4 of this is what? 265 is 66.25 or 66 torr. This one is 3/4. Contribution of B is 3/4 of 355. Yeah. Is 266. So if this were an ideal solution, then the vapor pressure would be the summation of these two. So it's 13, 332. So it should be 332 torr if it were ideal. So what kind of deviation do we have? We have a negative deviation. In other words, that curve is like this, right? Where we have one going this way and one going, let's see, one going this way. Yeah. So you add them together. Excuse me. Should be over here and over here. So this one should be the ideal. Perfectly straight. But it dips. So why does it dip? The negative deviation is due to the fact that when these are together, they are more attracted to each other than A is to itself and B is to itself. And that decreases the vapor pressure. So let's answer the question. This solution exhibits a positive deviation? No, it's a negative deviation from Rayleigh law. Okay. Hearing no arguments, we'll move on. All right, 12. Cucumber is placed in a concentrated salt solution. So we got a concentrated salt. I assume it's sodium chloride. And we got a cucumber in here with the seeds in it. So what dictates, what type of problem is this? This is osmosis. Right? Which way is the water going to move? Into the cells or out of the cells? If this is concentrated, more than likely, this solution is hypertonic to the cells, which means water's coming out. Okay, so that means A is the best answer. The water will flow from the cucumber to the solution, and it'll shrivel up or become flabby. All right, 13. Osmotic pressure depends on all but which of the following? Okay, osmotic pressure. What's the formula? Equals molarity gas constant, and temperature. Okay. So does it depend on pressure, air pressure, atmospheric pressure? I don't see a term in here for atmospheric pressure. We got molarity, like moles per unit volume, and we got temperature here, which has to be in K because of R is in K. So it depends on temperature, it depends on moles, and depends on volume. Atmospheric pressure, no, it doesn't depend on it. Molarity, yes. Temperature, yes. Ratio of moles to solution volume, it's another way of saying molarity. So atmospheric pressure is the one that has no influence on osmotic pressure. All right. So we got 14 coming up. Okay, shaving cream is an example of which colloid type? You remember your colloids? What's an aerosol? Aerosol is a solid or a liquid suspended in a gas. Right? So that's not shaving cream. Shaving cream is a gas suspended in a liquid, which is a foam. That's why B is the answer. What's an emulsion? Emulsion is a liquid in a liquid. A sol. A sol is a gas in a solid. When I think sol, I think those ceramic bricks that they used to put on the space shuttle. They weighed almost nothing. And I've seen some sols that you could heat to red hot with a blowtorch and then grab it by the corners and pick it up, no problem. Coagulate, that's not a type of colloid. That's what happens to a colloid when you destroy it. You make the particles bigger by clumping them together. And then they're so big that they won't stay in suspension any longer. That destroys the colloid. Moderate, here we go, here's a moderate. Moderate 3. Oh, I guess I should put this one as, so I can find it. It's E6. Moderate 3. I've only got 15 minutes. 0.2 molar solution of solute X is in, let's see, 0.2 molar solution of a solute X in benzene. 0.2 molar of X in benzene. Okay. Displays an osmotic pressure given by the formula pi equals 0.1 times RT. Okay, so this you know what we didn't add to that one? Equals IMRT. Remember that Van Hoff correction factor? We used it for other colligative properties. But this is for like molecules or associations that break apart. Right. So if it's like sodium chloride in solution, I would be 2, calcium chloride would be 3, sodium phosphate would be 4. But this one is a little weirder. If this is equal to these two terms, this is equal to I times M, and we know that molarity is 0.2, then what does I have to be? It's not a whole number anymore. I has to be 1/2. So if I is 1/2, it doesn't mean that the molecule is breaking apart. X isn't breaking apart. It's actually clumping together. right? So when you put it in solution, instead of X in solution, it's X2. It becomes diatomic. And B is the best answer. That was kind of tricky, I thought, because we've only studied things that dissociate, not clump together. I mean, we've looked at ion pairing, what effect it has, but we don't even know what X is. All we know is this evidence. If it's 0.2 molar that way, then this way it has to be half of that. All right. 4. Which of these solutions, 0.1 molal sodium chloride, 0.15 molal glucose, 0.1 molal calcium chloride, would have what? Highest vapor pressure, lowest boiling point. All right. So 0.1 molal sodium chloride, 0.1 molal sodium chloride versus 0.15 molal sucrose, or is it glucose? Glucose. Glucose and 0.1 molal calcium chloride. Okay, which one would have the highest vapor pressure? Well, this one, once we put it in solution, it's going to be equivalent to 0.2 molal because you've got 2 ions here. But this one's going to stay the same. Glucose does not dissociate. Okay, and calcium chloride would be 0.3 molal because it has 1, 2, 3 ions when it breaks apart. Okay, so the higher concentration is going to have the lowest vapor pressure. Right? Once you start putting non-volatile things into a solution, it decreases the vapor pressure of the solvent. So the lowest vapor pressure would be this one. The highest vapor pressure would be glucose. So this is vapor pressure for our answer. And the lowest boiling point. The highest boiling point would be the highest concentration. Right? That's our colligative property. So it would also be glucose. And that would be D. Right? Glucose satisfies both. What about this one? Same chemicals, same solutions, different question. So which one would have the lowest vapor pressure? Lowest vapor pressure would be the highest concentration. Right here, calcium chloride. And the lowest boiling point would be the lowest concentration, glucose. Because when you increase the concentration of solute, you increase the boiling point. So we want the lowest concentration. So it'd be calcium chloride glucose, which is C. Okay. I'm running out of time, sports fans. Let's see. 2, this is difficult 2. My goodness, we got 3 bad ones. I don't have time to do all of them. Okay. Decisions. I guess what we could do is let you do the lab. and get it done. And if there's any time left, I can come back and do these problems. Okay, because I don't want you to miss any part of the lab or run late in the lab just because I've got to talk. Maybe I've got time for one of them, like that. So let's do let's do 2. Is this difficult? This is difficult, isn't it? Yeah, difficult. And then difficult, I'm holding later to 4. 4. All right. So difficult 2. A solution is prepared from 53.8 grams of a non-volatile, non-dissociating solute and 85 grams of water. So we've got the mass of the solute equals 53.8. 53.8 grams. And the mass of the solvent equals 85 grams of water. Okay. The vapor pressure of the solution at 60 degrees is 132 torr. So the pressure of the solution at 60 degrees equals 132 torr. Okay, the vapor pressure of water at 60 degrees is 150 torr. Pressure of water at 60 degrees is 150 torr. Okay, and the question is, what's the molar mass of the solute? So we're looking for the molecular weight of solute, which would be the mass divided by the moles. So we got the mass already. What we need is the moles. So what we're looking at here is a colligative property having to do with vapor pressure. So the vapor pressure of the solution, vapor pressure of the solution is equal to the mole fraction of the solvent times its pure vapor pressure. Okay, so this is where we're going to get the moles of the solute, this relationship here. If we can find out the mole fraction of the solvent, then 1 minus that value is the mole fraction of the solute. Okay, so this would be 132 torr equals the mole fraction of the solvent times its pure, 150. So the mole fraction of water is equal to 132 divided by 150, which is 0.88. So the mole fraction of the solute is equal to 1 minus 0.88. Or 0.12. 0.12. Okay. You know what? We don't even need this. Because what's the mole fraction of water? If we let the mole fraction of water, in this case, is 0.88. What's that equal to? That's the moles of water divided by the moles of water plus the moles of the solute, right? So we've got the mass of water, we can calculate the moles, and then our unknown is the moles of the solute, correct? So how many moles of water do we have? Well, we need to divide it by 18.02 grams per mole. $85 divided by 18.02 is 4.717. So that's how many moles of water we have. So this is 4.717. This is 4.717 moles. So now we have, I'm going to bring that over here. And I'm going to put this times that. So we have 4.717 times 0.88 and then 0.88 times moles of solute. And that's equal to 4.717 over here. Okay, so here's our unknown. If we multiply these two together, 4.717 times 0.88 is 4.151. We subtract that from this side. We get 566, 0.566. So we moved all of this over here to that side right here. And that makes this 0.88 times moles of solute equals 0.566. So this one, moles of solute, is equal to that one divided by 0.88. 0.6432. 0.6432. That's moles of solute. So we've got mass of solute, and the molecular weight is here. So in here, this is equal to 0.6432. 53.8. 83.6 grams per mole. Is that right? Yeah. Had me worried for a minute. But to solve this problem, we just need two things. To understand what molecular weight means, then you go looking for the information. Okay, we got that one already. That's good. Now we have to figure out how we find moles. Well, based on what we have, we're talking about Henry's law. I think it's Henry's law, isn't it? And first one we're going to do is chapter 11, easy 6. So let's go back. Oops, did I go too far? No, I didn't go far enough. $11 easy. Okay, now we'll go down to 6. There it is. Okay. So for this problem, we'll go back to the 3-step process for forming a solution. So the total energy, the heat of solution, is equal to these 3. And the first one, let me use the terminology they use. The first one is lattice energy. lattice energy. That's how much energy it takes to pull the atoms apart, pull the ions apart. The second and the third one, well, this is also called solvent expansion. In other words, make a hole. And this one is what's the word? Solvation. This is solvation, where the solvent and the solute start to form their bonds. Okay. So the question is, with that information, and I'll write that information up here in a second, but the question is, which salt forms stronger attractions with water? Well, the information that we're given doesn't break out this attractions with water part right here. So what we're actually given is a combination of the two, and it's called the heat of hydration. Okay, so what are we given? Well, we're given that the lattice energy for Kf, I guess I put it down here, Af, lattice energy, delta H lattice equals minus 804 kilojoules per mole. Okay. And the lattice energy for rubidium fluoride is minus 768 kilojoules per mole. These would be comparison in that position right there. Let's see. Okay, the lattice energy, I'll just put one of them up here. The lattice energy in this case is, remember, the K ions as a gas plus the fluoride ions as a gas yields the solid. Okay, but we're doing just the opposite here, right? This gives up energy, that much energy, when these come together and form that. So that means we've got to reverse the sign in order to fit it in here. Okay, and do the same thing for that one. All right. So I'm missing some information. Let's see. Oh, here it is. The heat of solution for Kf. The delta H of solution for Kf is minus 15 kilojoules. And for rubidium fluoride is minus 24. Yeah, kilojoules. Okay. Now the question is, which salt forms a stronger attraction with water? Well, this is the one we're trying to get at. Right here, this part. But notice, if we're just comparing the two, and the solvent expansion, the solvent's the same for both of them. So this is going to be constant for both of them. So if we can find a value for this and compare it, it will answer our question. Since this doesn't change, then the difference between the two would be due to that. So what we need to do is say the heat of solution for let's see, lattice energy. The heat of solution, yeah, here it is. This heat of solution is equal to the negative lattice energy. Negative lattice energy, 804. I'm going to leave out the units because I don't have enough room. Plus, and let's just call this one delta H KF. It's this value right here. And this one is its heat of solution, which is equal to a negative 768 plus its delta H of this hydration, and we'll put rubidium fluoride. Okay, so we've got this expression is equal to that expression. So if we say minus 15 equals a plus 804 plus delta H, then delta H for this one, this delta HKF for this one is equal to minus 15 minus 804. Okay? Did I lose you? Well, that's kind of down below. Oh, that's kind of confusing. Let me do it this way. Let's spread it out. Let's go over here like this. Equals minus a minus 804 plus delta H for the KF. Then I'm going to leave this one on that side of this equation. And we'll put this one, which is positive here, but now it becomes negative on this side. Minus 15, negative 804 equals a negative 819 kilojoules per mole is equal to the delta H for the KF hydration. Okay, I'll do the same thing on this side. And this one should be 24 minus 768 equals 2,189 a minus 792 kilojoules per mole. And this is equal to the delta H hydration for rubidium fluoride. Okay. So which one has the stronger attraction for water? Well, when they come together, you give up energy, right? So the sign's going to be negative. The bigger the negative, the stronger the attraction. Since that's the same for both of them, then it has to be due to this one. Okay, so this one is a negative 819. This one's only a negative 792. So this one's a bigger negative, and this one has the stronger delta H of solvation, stronger attraction to the solvent. Whew. All right, so now that one's done. We need D4s next. Okay. Difficult 4. Where's the difficult? Here's the medium. Difficult. Here we go. Actually, this one's not too bad. So you've got a 10.4 gram mixture of table sugar and table salt. So we've got sucrose plus salt. And the mass of the combination is equal to 10.4 grams. When this mixture is dissolved in 150 grams of water, so the mass of water, which is the solvent, is equal to 150 grams, the freezing point is found to be minus 2.24. So this solution, the freezing point, T freezing point equals minus 2.24 degrees C. So what does that mean for the delta T? How did the temperature of water, the freezing point of water, how did it decrease? Because this is freezing point depression. Yeah, the change in temperature is 2.24, right? Because it's supposed to be 0. Okay, so we got that change in temperature. What's the percent by mass of sugar in the original mixture? Let me see. I don't want to flounder around, so I'm just going to look at it this way. Okay, so what we're looking at is this equation, and this is equal to the Van Hoff correction times K for water times the molality. Right? But we don't know the molality yet. That's just our starting point. We do know that the I for sucrose equals 1, and the I for the table salt is 2. Okay, we know that. We are going to need to know the molar mass, right? Because this is molality. So we got to know the molar mass of each one of these, and we got to be able to calculate the moles of each one. Only we're not going to do it directly. Mathematically, we're going to do it algebraically. So what's the molar mass of sodium chloride? Well, let's see. Sodium is, I can't read that one. It's too far away. Sodium is 23.00. Chlorine, I know that one, 3545. So we get 5,485 grams per mole. Okay. Sucrose. Well, sucrose is C11H214 I believe. Let's be sure. Yeah. So this is going to be 12 times 12.01 for carbon. It's going to be 22 times 1.01 for hydrogen, and 11 times 16 for oxygen. I can't need my calculator for that one. Let's see, 12.01 times 12, and then 22 times 1.01, add that in, and then 16 times 11, add that in. 342.34. Okay, so there's our molar masses. All right. Now comes the tricky part. The change in temperature is additive. In other words, there's a change in temperature due to the sucrose, there's a change in temperature due to the sodium chloride, and the effect that each one has is additive. So this change in temperature, the total change in temperature, is due to the change in temperature for sodium chloride plus the change in temperature for sucrose. So we can set up a separate change in temperature for each one. Right? So the total change in temperature is going to be equal to the I for sodium chloride times the K for water times the molality of sodium chloride. And same thing for sucrose. The I for sucrose times the K, which will be the same value, and then the molality of the sucrose. All right. So we can fill in some values here. What's the K value for water? It's 1.86 degrees C per molal. So if we expand this, then we got for sodium chloride, that value is 2 for I, and then 1.86. I'm going to leave the units out. And then this is molality is the moles of sodium chloride per 0.150 kilograms. Okay. That's the molality for sodium chloride. This one is I equals 1 and 1.86 is the same. And then this one is the moles of sucrose per 0.150 kilograms. Okay. Now we have something we can work with, sort of. We've still got the temperature change, and I haven't put it in here yet because I'm not finished. But the problem is now we have two unknowns. We got moles of sodium chloride and moles of sucrose. But let's partially solve this equation. This is 2.24 degrees C. Right, that's the change in temperature. So if we factor these two things out right here, this one and that one, it's the same for both of them, right? So we can bring this much out, and we can say 2.24 times 0.15 over 1.86, right? Because this goes into the denominator, this goes into the numerator, times this value. And what does that leave us? That leaves us 2 times the moles of sodium chloride plus 1 times the moles of sucrose. Okay, so let's reduce that side to a whole number. Let's see, 2.24 times 0.15 divided by 1.86, and that's 0.1806. Right, and that